Here we are going to discuss about the transformation of our frame element. Before going to the transformation of frame element, let us first discuss how we applied our transformation matrix for a truss element. In case of truss, we have learned that truss element normally is to orient in different angle, and since the member are orient in different angle, it is important to transform all the stiffness matrix according to our global direction. Okay, so once we transform all the element matrix which is axial in nature in their own axis systems, that we need to transform according to our global axis system so that we can assemble it. Now in the truss, if we consider 2-degree freedom systems, in that case we have learned that we can correlate our force and the displacement in this way. So here this is our force that is equal to K times U. So K is your stiffness matrix. Okay. And you can see that if this is your first degree and if this is your first node and second node, other way, if this is your first degree freedom and second degree freedom, this is your first degree freedom and this is second degree freedom. Here we are considering 1 degree freedom at each node. Okay, so our size of the stiffness matrix will be 2 by 2, and we have obtained this is your K11 and this is your K21 and this is your K22 and this is your K12. Okay. Now, if we consider 2 degree freedom at each node, 2 degree freedom in the sense 1 degree along the axial deformations, another degree we are considering which is perpendicular to this axis. So we are considering 2 degree freedom U and at each node. Okay, so if you have 2 nodes in the truss element, then our size of the stiffness matrix will be 4 by 4. Here you just see orientation of this truss element. Here you can see the orientation of the truss element is horizontal, so theta is 0. Okay, so this component V component will be 0. Okay, so the 2 by 2 matrix we can write in this way. So here you can see what we have done. Here you can see this is your 2 by 2. This is V component in 0. Okay, so we are first writing the force acting along the V degree freedom is 0, force acting at V degree of freedom 0. So this is V, basically force acting on the V degree of freedom at ith node and force acting at the V degree of freedom at jth node, both are 0. And we are just replacing this value into 4 by 4 system. So here we are getting K11 or Kii, here minus Kij, here also minus Kij, Kjj, and rest of the value are 0. So here you can see that component corresponding to V degree freedom are 0. So basically we are rewriting the same matrix 4 by 4 size stiffness matrix. Initially we had 2 by 2 size, we are just rearranging into 4 by 4 system. Here you can see our axial direction is along this U and the V. So here we are writing X and Y. Okay, and we have the relationship with the force and the displacement in this way. Now, if the truss element is oriented in some angle, for example, theta angle, okay, then our axial direction for the truss will be in this direction. This is the axial direction of the truss element. Now, initially it was in this direction. That time our axial direction was like this. Now it is oriented in some angle theta. So this is our present axial direction. So what we are doing, we are saying this is your x dash coordinate systems. Okay, so initially we have x and y coordinate systems. Now our coordinate systems change to x dash and our y dash. Initially this angle was 90 degree. So after the transformation also this angle 90 degree. So X dash and Y dash here is now a local axis system. You will be confused why I am discussing transformation of truss element, but you just see that transformation of truss element and the frame element is very similar. Only thing is that the frame element, our size of the transformation matrix will be 6 by 6, and that also very easy to understand once you understand this transformation matrix. Okay. So what we are doing here, we are considering this is our local axis system. So what we are doing, instead of writing at ui, vi, uj, vj, I am writing in terms of u, I dash, vi dash, uj dash, vj dash. Okay, and this is our same stiffness matrix. Writing it here. Since our local axis systems is our I in the dash direction, okay, x dash and y dash direction, x dash and y dash direction, the force also will be in the local direction. We're writing x, writing as your fi dash and fj dash. Same thing, what we have learned here, we're writing same thing here, only we have changed from uv system to u dash v dash coordinate system. uv coordinate system to u dash v dash coordinate system. So now we're writing in a simplified form as like this, u as your k u dash that is equal to f dash, k u dash equal to your f dash. Okay. Now we have to find the relationship between u dash and u. We have to find the relationship between u dash and u. Okay. So basically you can say that u dash that is equal to transformation matrix into u. We are writing in this form. Okay. Now we need to find what is the how the transformation matrix look like. How the transformation matrix look like. Okay. Now here we just see what we are going to do. We are going to identify how the transformation matrix look like and what is the size of the transformation matrix. Okay. So here this is our x dash and y dash direction, and this is our x and y. Okay. Now here you can see ui dash. Ui dash, that means we are considering u component in the ith node. We are considering u component in the ith node. So here you can see ui dash basically corresponding to two direction, corresponding to the axial direction here. Okay, ui dash, u dash, sorry, ui dash is basically corresponding to axial direction in the ith node. So here you can see that is ui times cos theta. Okay, so we are getting contribution from this ui. Okay, if we consider a small strip here, if you consider a small strip here, whatever the ui component is there, that will come here as your ui cos theta, and from this to have vi sin theta. So this angle is theta, so this angle also is theta. Okay. So here in the ui dash, here ui dash, if you consider a small strip here, okay, that will be equal to your ui cos theta plus your vi sin theta. Okay. Now if you consider your vi dash, you consider vi dash, that means v component the ith node. Okay. Here you can see that we are getting this component here. So here if we have your ui component, so here this component here will be ui sine theta. Okay, and from vi component here we will get vi cos theta. Okay, now here this side we have considered as a positive reaction, so this side, this part will be positive. Okay, this part will be positive, but this part will be negative. So here we are writing minus ui sine theta minus ui sine theta plus vi cos theta. Similarly, if we consider jth node and if we consider a small strip here, okay, we can identify the similar relationship that we obtained the ith node. Okay. Now, what we are going to do, we are writing u dash, we are writing ui dash, vi dash, uj dash, vj dash in a vector form, and we are writing ui, vi, uj, vj in this vector form, and here we are writing cos theta, sin theta in matrix form. So now here, if we say this is, you can say this is our transformation matrix, this is our transformation matrix, and u dash that is equal to transformation matrix times u. So u dash that is equal to transformation matrix times u. Okay, so you can write k u dash f dash that is equal to k times u that is equal to your t times f. Look at the force also here transforming. So here you can say this u is now according to our global coordinate system, if also according to our global coordinate systems. Here u dash was local coordinate system, f dash was in local coordinate system. Now here you can see from our local coordinate systems we have changed to our global coordinate systems. Okay, so here till now we are discussing about your transformation matrix for the truss element. Okay, now one more thing, one more mathematical simplification we are going to do here. So we have obtained here that t times k times tu that is equal to tf. Now if you multiply both the side with t transpose, okay, if you multiply both the side with the t transpose, we can obtain like this t transpose kt u that is equal to t transpose t times u. Okay, so if you multiply t transpose t, you are getting as identity matrix. So here we can say that t transpose kt times u that is equal to f. So here we can see that we are writing t transpose kt as your k dash. So initially we obtain k times u dash equal to f dash, where u dash and f dash was in our local coordinate systems. Okay, after some mathematical simplification, we obtain k dash times u that is equal to f. So now here you can see that u is in our global coordinate systems, f also in our global coordinate systems, and if we multiply initially obtain k matrix with t transpose kt, we are obtaining our k dash matrix. Okay, this is the relationship we obtain for a class element. Now, if we consider a frame element, we will observe that we are getting very similar matrix. Only thing is that our size of the stiffness matrix, size of the transformation matrix has changed. So here you can see in the class element we used to have this degree. Okay, in the truss element, we used to have x and y. Okay, so that displacement along x-axis we used to write as u, and displacement along y-axis we used to write v. Here we are writing u1, u2, and another degree of freedom we have, that is rotation. Here, if you consider a frame element, and if the frame element is lying in horizontal direction, so what we can do, we can consider this is our x direction, this is our y direction, and this is our rotation. Here also x, y, and our rotation here. Okay. Now, if this frame element rotate at an angle theta like this, okay. So for the frame element, now our axial direction will be in this direction. Here u dash, u1 dash axial direction, Here, this is a U4 dash. Initially, we used to have U1, U2, U3, but here, fourth direction is corresponding to axial direction. So, this is now our axial direction. And initially, we had U2, here U2, okay, U2 here, Y, that is your U2, that is now U dash, okay. But that rotation here initially, which was your U3, now also is to be U3 dash, but that value will be the same. Okay, so though we have one extra degree of freedom corresponding to rotational degree of freedom, that value is not going to change. Okay. So what will happen if we consider that for a truss element we used to have U, V, Ui, Vi, Uj, Vj. Okay. Here for the frame element we have another extra degree freedom corresponding to rotational degree freedom. That value in the transposal matrix, that value will be 1 here and 1 here. Okay, so now if we rearrange for total 6 degree freedom system, so our transposal matrix for the frame element will be 6 by 6. Only thing is that our third diagonal terms and the sixth diagonal terms will be 1 and rest of the value will be 0 here. Initially we just see we have cos theta, sin theta, cos theta, sin theta, minus sin theta, cos theta, minus sin theta, cos theta. Rest of the value is 0. Here in the third degree freedom, we have 1 in the diagonal term, rest value is 0. And earlier we used to have cos theta, sin theta, minus sin theta, cos theta, sin theta, minus cos theta. That value are getting it here. And in the sixth degree freedom, which is corresponding to rotational degree freedom, which is corresponding to the rotational degree freedom, that diagonal term is coming 1. Okay, so now here we can see that for a frame element also we can easily obtain our transposal matrix. Okay, and the transposal matrix will be of 6 by 6 size, and component in the transposal matrix will be the same. Only thing is that in the diagonal terms we will have, in that diagonal term corresponding to a rotational degree freedom, we have 1 value, magnitude of identity value 1. Okay, and the rest of the value is the same. Only our degree freedom has changed. Only our degree freedom has changed, but the component are coming at the same. Okay, similarly, obtain the transposal matrix for a frame element. Okay, we have discussed all the basics for solving a frame problem. Okay, now onwards we are going to see how we can solve this frame problem, solve this particular frame member where we have 2 number of elements, and at each node we have 3 degree freedom. So we used to have total 9 by 9 matrix size. Okay, and here you can see that one member is oriented in some angle. This is horizontal, this member is vertical in nature. So this member is oriented in some angle. We are going to see how we can apply the transformation rule, and how you can obtain our local matrix in our global coordinate systems, and how you can assemble it, and how you can apply the boundary condition, and how we are going to solve it.